Okay, now Hall effect. So first, before I talk about Hall effect, let's recall briefly about semiconductor, because to understand Hall effect, you need to understand semiconductor first. So semiconductor, what is it? So let's compare to conductor and semiconductor. Basically, it's metal and semi-metal. So metal, let's take one example, sodium metal. So you have 281. Here's the nucleus. 1, 2, 3, 4, 5, 6, 7. And then one valence electron. Okay. One valence electron in the outer shell. The more electron you have in the outer shell, the stronger will be the force of attraction, the harder for the electron to leave the atom. So if you have only one valence electron, it makes it very easy for the electron to just pop out and become a free electrons. That is why metals generally they have a lot of free electrons. This electron here, it can be, we categorize the electron into two groups. First is the valence, and then we have the conduction. Valence electron and the conduction electron. Conduction is just another term for free electrons. If it's a conduction electron, then it is a free electrons. When I apply potential difference, then it will start moving. It will produce current. So it is the conduction electron that produces the current. Okay, that's first one. Valence electron, what do? They do not produce current. They have only one job. What is the job? Do the pairing. When one atom matches with another atom, they do bonding, the pairing of the electrons. That is done by the valence. The conduction is responsible for current flow. The valence does not responsible for the current flow. Okay? So, in metal, these valence electron, they can be, this is special, unique characteristics of metal, is that the valence electron, they can actually become a conduction electron and become valence electron. It's like they can pop between these two. Okay, if you apply potential difference when necessary, when needed, when you're in need of electron, they can come out. They can jump from valence to conduction. They can also go back from conduction to valence. That is very unique property, only found in metal. Okay, so that's one reason why metal always have ready electrons, and they are a good conductor of electricity. Now let's compare with semi-metal, semiconductor. Okay, semiconductor, they have 4 valence electrons. Okay, so let's do only the outer shell. You have more electrons in the outer shell. The forces of attraction is stronger. It makes it harder for this electron to leave. That means it makes it harder for the electron to become a conduction electron. You need to supply energy, enough energy for this valence electron to pop out. How much energy you need to supply? That forms a gap. Let's say you want to supply, the requirement is 100 joule. You only supply 80, is not enough. So electrons still stay here. Only when it is 100 or above, then it can jump out. So we say that there is a gap. There's a forbidden gap that is preventing the electron from becoming a conduction electron. What is the gap? The gap is the amount of energy you need to supply. Okay, so how do you supply the energy? You can supply energy by heating. So the more energy you supply, the more conduction electron. So for this valence electron, if it wants to become a conduction electron, it needs to absorb energy and go to higher shell. When it goes to higher shell, then it goes from valence to conduction. Now, if we compare at room temperature, at constant temperature for these two metals, metal and semi-metal, which one has more free electrons, conduction electrons? Metal will have more than the semi-metal. But if at high temperature, Okay, if I keep increasing the temperature, then you will have more and more electron jumping into the conduction band, and thus semi-metal will become a better conductor at high temperature. That is why semiconductor is used in electronic chips, all that, laptops, phones, all that. Okay, now every single electron, they have energy. If I classify, if I take, okay, this electron, how much energy you have? I plot it on a graph here. This energy level graph is separated into two. Here, we call it the valence band. And then slightly above, this is the conduction band. Notice that for metal, right, the valence band and the conduction band, they overlap. This part overlapping means that if I say that, okay, this electron, where does it belong in this graph? This electron belongs to here, then this electron, it can be in the valence, it can be in the conduction. All these electrons in this region, they automatically become a conduction electron when needed. Okay, but if I compare to semi-metal, here's the valence band. Think of it like energy. So this is low energy. Conduction is high energy, higher in the graph, right? So conduction band is here. It is separated by a gap. Here is conduction. Conduction band. At 0 temperature, 0 Kelvin, absolute 0. All the electrons, they are at valence. No one is in the conduction band. When you increase the temperature to 300 K, that is room temperature. Okay, in our normal temperature, room temperature, some of the electron will go to the conduction. And if you keep on increasing this, more and more electron will go up. Okay, so if you compare how many free electrons available, this one is more than this one. So we say the charge carrier, CHA, charge carrier per unit volume. Okay, per unit volume of metal is higher than semi-metal. Okay, take note of this, because later when I go to the Hall effect, you'll see why this is. This affects the Hall effect. Okay, so what is the takeaway for this one? Charge carrier of the metal, or we say the conduction electrons of metal is higher, okay, per unit volume is higher than semi-metal. Now, for semiconductor, the most common one is silicon. Okay, where do you find silicon? Okay, it is found naturally in the rocks, in the Earth's crust. Okay, the rocks contains a lot of mineral. So if you extract the mineral, you only take the silicon mineral, extract everything together, you put on one side, you group them together, you get a pure silicon. So a pure silicon, here I will write, this is the lattice structure. Okay, let's do this. Okay, if my computer is blocking you, you find your space. Okay, find your space. Now here, one more row. You extract the mineral from the rocks, put it together, you get this pure semiconductor. Okay, pure semiconductor means that they are all the same nature, all the same elements. Okay, then we have a semiconductor here, right? So semiconductor, now I can replace one atom of the silicon. Silicon, how many valence electrons? But 4, right? 4. So they do pairing with 4 other atoms. That's why I draw like this. One sharing with this one, sharing with this. One line represents 2 electrons. They are sharing this one. Okay. If I remove the silicon atom and I replace with, let's say, aluminium. Okay, now aluminium has 3 valence electrons. 3 valence electron. Silicon is 4 valence electron. So if I replace with aluminium, then there's 1 electron missing. 1 pair with this one, 1 pair with this one, another 1 pair with this one. This one, how about this one? This one is missing, no electron pair with it. So I will create a hole like this, like a vacancy. A vacancy, this is like absence of electrons. When there's electron flowing nearby, that electron will be attracted by this one. If electron is a negative, the absence of electron is a positive. So this is a positive charge. We give it a name, we call it holes. Okay, holes. So when I say holes, then you know it's what? Positive charge carrier is a positive charge carrier. I change 1 atom, then I get 1 extra. I get 1 hole created. If I replace 1 more atom here, make this aluminium again, then again this one, we've got another hole here. Holes. You got 2 positive charge. Now, I want to make this very clear, is that what is the charge of the overall semiconductor? Does it mean that I have make it positively charged? No. The overall charge, the net charge of the conductor is still neutral. Because if you think about it, before I add the aluminium, let's say it is silicon, right? What is the charge? Number of electron is the same as number of proton. It is a neutral charge. Aluminium, what is the charge? Number of electron is the same as number of proton. So this is also a neutral charge. You take 1 neutral, add with another neutral, you get neutral also. So the charge of this thing, of this semiconductor, is a neutral. Okay, doesn't mean that if it has holes means it is positive charge. No, it is still neutral charge. It is because of the arrangement that makes it produce this 2 positive charge. It's because of the arrangement. Okay, but if you calculate like the number of electron and the number of proton, it's still equal. It is still equal for the material. Okay, so it's just that the arrangement create 1 positive charge carrier. Okay, I'll write it here. The arrangement creates the positive charge carrier. I put 1 million aluminium atoms, then how many holes I get? 1 million holes. So they can calculate based on how many holes they want to create, they put how many atoms inside. Okay, now here I got hole, then let's say I apply a potential difference. Okay, so you think of this as a material, a huge piece of semiconductor. Okay, this is just showing the internal structure. And here I connect to potential difference. This is negative. This is positive. Then what will happen inside here? The holes is positive charge, right? Here you have a negative. So this hole will get attracted towards the left. They will start flowing here. This hole will start moving to the left. And when you have a flow of charge, whether it be negative or positive, you have current. So this one creates flow of charge, creates current. Such semiconductor is called a p-type. Okay, this is what you want to remember. P-type semiconductor. P means positive. Why positive? Because you have created many, many holes. So your majority charge is a positive charge. That's why we call it P-type semiconductor. P-type semiconductor, how do you create it? You mix with aluminum, or you mix with any atom that has only 3 valence electrons. Okay, so take this down. I'll write down here, P-type semiconductor. What we need to know, majority charge is the one that they always ask. Majority charge is what? Positive. False. Net charge, 0. Okay, net charge is 0. Majority charge is positive. Okay, let's say I take the same piece of material, the pure silicon, okay? This time I mix it with another element. Instead of mixing aluminum, I put an atom that has 5 valence electrons. This one is less than silicon, right? 1 electron less than silicon. What if I put 1 electron more than silicon? Okay, for example, phosphorus. I change this one to P. How many valence electron phosphorus? 5 valence electron. Si is 4 valence electron. So if it has 5, 4 is shared with other 4 silicon atom, and you got 1 extra. 1 extra, okay, I put it here. This extra, automatically it becomes a conduction electron. I add another phosphorus atom. I get another conduction electron. I add another one. I get another conduction electron. What is the majority charge? The majority charge, now it is the negative charge. So again, think of this as a piece of semiconductor, majority charge, carrier, negative charge. And what we call this type of semiconductor, we call it negative, right? So N type. N-type semiconductor. So you got 3 types. In general, you got 3 types of semicon. One is the purest one. The one that I straight away extract from the ore, from the stone, from the rock. I get the purest one. And then we got the other 2 is the processed one. I add this, I make it become P. This one, I make it become N-type. So what we need to remember, it is the majority charge that we need to remember. And also the charge, overall charge is neutral charge. If I connect to a potential difference, here, positive, negative, then it will start attracting the electron. The electron will start to flow. Why is it not the holes that is flowing? Because the majority is electron, right? So electron is the one that's flowing. Electron flow here, flow here, flow here. But this one, it is the hole that is flowing. But both creates current. Both create current, same. The effect is the same. Okay, so that is a short one, like a recall. A brief one on the semiconductors. At normal temperature, conductor, the metal is a better conductor. But at higher temperature, semicon become a better conductor. Why? like the electron at higher temperature, they all move to conduction band. So in short, higher temperature, the semiconductor, they create more free electrons. That's why they are better conductors at high temperature. Okay? Right, now let's enter the Hall effect. Huh? Okay, suppose that there is a semiconductor, and then I cut only a thin slice. Okay, so it's like a rectangular semicon. I cut only one slice, and I take out. This is the one you see on the board. It can be two types, P-type or N-type. Okay, now again, P-type, let's say we choose one first. I will show you if it's P-type, what happened, and if it's N-type, what happened. Let's take N-type first. So this is N-type semicon. What is the majority charge carrier? This is electrons. Majority is negative. I take a thin slice and then I connect to a wire. Connect to a potential difference, and then current starts to flow. Let's say positive. Let's say current flow, current direction here, I. Here, and then here. The moment I connect to the potential, what is happening inside? Inside this thing, this semicon. What is happening inside is what I've shown earlier. The charges move, right? All the charges starts to move. So in this case, it is the electron, it starts to move. Where is it moving? Current is flowing here, so electron moves opposite direction. So all these majority charge found inside here, they start to drift. They start to drift. So here I show electron. They are having a drift velocity v. Now, I place this in a magnetic field. So I take these lines, I connect to the wire already, and then I place it in a magnetic field. How do I place it? I place it normal to the magnetic field. So the magnetic field comes in this direction. Okay, so this direction, we call this B, okay, B field. is making 90° with the surface of the semicon. The velocity vector is also making a 90° with the field. The moment I put it in the magnetic field, what happened? Okay, we have learned force on a moving charge. When you have a charge moving in the magnetic field, what causes the magnetic force? You must have a moving charge. If the charge is stationary, do you have the force? You do not have the force. The moment it starts to move, okay, the magnetic force acts. Okay, now, where is the force acting? We can find using our Fleming's left hand. Okay, so again, you have to think of 3 dimensions. This is our force, this is our field. So the index finger point down, okay, and then your current, where is it pointing? Current is pointing to the back. The easiest way to think of this is, imagine I see from here, okay? I see from here. That means this is the side that I'm seeing. If I see from here, how does the field look like? The field is straight down, D. What is the current flowing if I see from here? This is away from my eye, so this is X. Okay. This is 2D if I see from here. Okay. I see from here, magnetic field down, and then this is the current flowing away from my eye. Okay, let's do Fleming's. Index finger down, middle finger to the board, and then your thumb is left side. Okay, like this. So index finger down is the magnetic field. This one is into the page, and then your thumb is left side. So the force is here, left, F. I will write it FB, force due to magnetic field. This is in my diagram here. If I want to relate to my 3D diagram, where is the force acting? Force is acting to the left. This is like towards AECG. Okay, I'll write here. Force acting towards AECG. Okay. What happened next? You have a force acting on the charge towards AECG. So the charge will start moving to the side here. You'll see a curved trajectory, all move to this side. When they come here, all these electrons come here. There's a buildup of electron. So here you get negatively charged. Which side gets negatively charged? AECG, this side, negatively charged. What causes the charge to build up? It is the magnetic force that causes the charge to build up on this side. Okay, when the electron goes here, all the electron leaves, they go away from this side, B, F, D, H. Then what is the charge of this side? When all the electron leaves, then you have absence of electrons. Automatically, that will become a positive. This one will become positive, positive, positive. It's like you take a sphere, a metal sphere, and then you take a positive rod. This one will attract all the negative here, but then the positive will go to one side. So two charges is created. It's same as what happened here. Okay, so the moment you put into the field, all the charge starts to move already. Okay, the moment you put inside, then all the charge starts to move. They slowly build up. They keep building up until a certain point. This side becomes large, very, very negative. And what happens next? You have a negative, you have a positive. These two will set up an electric field. Okay, so I write down here, electric field. Electric field is set up. Where is the electric field pointing? Always from positive to negative. Negative, positive. Field is pointing positive to negative. Again, the electric field at first is not there. Only when they accumulate, they build up, then slowly the electric field will build. Okay, because of this one. More and more electron move to that side, becomes more negative. This one becomes more positive. Then the electric field build up, and then the strength of the electric field also increases. Okay. More and more charges, then the strength of the electric field increases. Now, when the electric field build up, the next electron that is coming out from here, what happened to him? What happened to the electron? When the electric field build up, the next electron coming here, it is subjected to what forces? Okay, this is the electron. This is the drift velocity. Okay, you have first FB, right? So FB to the left. This FB, okay, first, this FB, is it changing or is it constant? This FB is a constant. Because what is the formula FB? BIL. Okay, BIL. This is a constant. The strength we do not change. The current we do not change. The L, same. This is a constant force, FB. And then we have one more force acts on this electron. When the electric field is there, what will happen to the electron? This electron will be attracted to the right side because you have positive charge here. Okay, it will be attracted to BFDDH. Okay, electric field set up. So we write here electric force acts on electron towards BF DH. Okay, so one force is F electric. Is this a constant force? Who is producing this electric? This is produced by the field, and it depends on the field strength. The field strength depends on how many electrons build up. That means it is not a constant force. As more electrons build up, this is going to increase. Okay, so as more electron build up, more electron build, what is the next one? More electron build electric field strength. Okay, this is a keyword. In the exam, when you're asked to explain, you're going to put as many keywords as you can. Electric field strength, that is one keyword. Electric field strength increase. More electron build, electric field strength increase. So electric force increase. Electric force increase. But FB the same. FB same. Okay. This one increased, this one same. So eventually this is going to be equal to this one. FB will be equal to FE. When this happens, electron stop building. Why stop building? Because this one is equal to this one, the electron go in a straight line. When this has been achieved, now this one keeps flowing like this. There is a fixed amount of charges here on both sides. This will create a voltage. If I connect a sensitive voltmeter, millivoltmeter, connect to these two sides. Which two sides? Very important. AECG, AECG, and BFBH. BFBH. I connect a voltmeter, millivoltmeter. The value is going to be very small. You'll get a reading. Okay, here you will get a reading of the voltage, but it's a very, very small value. And later we'll discuss how do we make it large? How do we increase the value? Okay, this voltage set up between the two phases. These two phases are parallel, right? They are parallel. So we can sometimes call it parallel plate. These are the parallel plates. There's a reading in the voltage, and this voltage, we call it Hall voltage. Yeah, so you got voltage here in the wire. That is one voltage, right? That is from the circuit. The wire that you connect to the voltage of the circuit. At the same time, you also have another voltage that is at the side. These two sides. That is the Hall voltage. So what is the Hall effect? We can define the Hall effect here. Hall effect. It is a phenomenon when I allow current and magnetic to flow through the semiconductor. Basically, it means if I take any semiconductor, okay, the P-type and the N-type, I allow magnetic field to flow through it, I allow current to flow through it. Like that only, I get a Hall voltage. That is the Hall effect. Okay, I take a semicon, I allow current and magnetic field, then it will produce the Hall voltage. Explanation is over here. Okay, now we will look at the mathematics for this Hall voltage. We derive an equation for the Hall voltage. And also practically, what do we do to measure this Hall voltage? Okay, I will erase this section. Okay, from here, we get what? FB equals to FE. Start there. FB equals to FE. What is the force? This is the force on a charge. So BQV. There's no sign beta because everything is normal here. BQV equals to QE. This is from your electric field chapter. Force equals to QE. Okay. Now, from here, just now we mentioned these two plates are parallel plates. It's like parallel plates separated by a distance d. Okay, which plate? The sides. Okay, AECG and BFDH. They are parallel plate separated by the distance. What is the electric field strength? Again, this is from the electric chapter. E equals to V over D. The electric field strength can be calculated by taking the potential difference between the plate divided by the separation of distance d. Okay, what is the d here? Be careful of the dimension because during the exam, the field can come from here, come from here, come from here. Later, I'll teach you one method to see how to find all this easily. Okay, but see here first. The d here, which length is this? Distance between the two parallel plates. That is the AB. Okay, the D is the AB or the CD. Here, this is the AB. Okay, cancel, cancel. BV equals to V over. This is voltage V over D. dBV equals to okay. I switch position. V equals to dBV. That's the drift velocity. The potential difference, this V between the parallel plate is also known as Hall voltage. So this is VH equals to dB. Okay, now in my equation, I have this one, drift velocity. Okay, I equals to NE, A, drift velocity. The drift velocity equals to I over NA. Put it inside, we get dBi over NEA, VH. One more step. I want to cancel the D from my area. What area is this? This area is from where? From here, right? The drift velocity equation. What is this area? That is the cross-sectional area. Cross-sectional area, which is the front face. This is the cross-section. Because your current is flowing like this, sorry, like this. The current is flowing like this, then what is the cross-section? This is the cross-section. A, B, C, D is your cross-section. So area is equals to, can I derive an equation? Can I write an expression of A in terms of D so that I can cross off this one? So area of here is D times into D times into. Okay, I can write like this first. Easier, we can see is AB times BD. Okay, AB times BD. So D times BD, we assign a parameter, we call it thickness. Here, where is the thickness? This is the thickness. Okay, put it inside. D, VI, and E, and then DT. Cross, get BI over NET. By over net. By net. Calculation should be no problem. You have the formula. Okay, just find the parameters here. Now, from here, the formula is given in the formula sheet, okay, in the paper form. But then you need to know the quantity. B is, again, come back to B. What is B again? This is from your previous chapter. Magnetic flux density. That is like magnetic field strength. Magnetic flux density. Tesla. I, current, okay. E, charge. T, thickness. Now, I want you to remember it this way. The T is always parallel to the B field. What is B field? B field is the magnetic field, okay? You look at where is the magnetic field coming. Magnetic field is coming like this, straight down. Where is the thickness? The thickness is parallel to the magnetic field like this. Okay? So, if I change the magnetic field coming in this way, then which one is your thickness? This one is your thickness. If your magnetic field is coming in this direction, your thickness is this AB. Okay, in this example, coming down, your thickness is this one. So we write here parallel to the B field. This is, okay, faster, you can identify, because I can give you a square. This one rectangle, sometimes if they give you a square, where is the thickness? Or if I rotate this magnetic field from here, anyway, current I can also change. Where is the thickness? Okay, you see the magnetic field. Parallel to the magnetic field, this side is the thickness. Okay, that is the one that we put in the equation here. And this is number of charge carrier per unit volume. This is the N that we are talking about earlier, the metal and the semi-metal. This metal has more charge per volume or semi-metal? Metal, they have more number of charge per unit volume. That means metal, they have bigger N. Their N is bigger than semiconductor. And later we'll look at why we use semiconductor but not metal. Can we use metal for this one? Yes, we can use metal also. But how will it affect? The reading of the Hall voltage will be very, very small. Sometimes it's undetectable. Okay, later we'll come to that. Okay. BI, okay, BINET. Now, let me write it here. BH, BI over NET. Okay, why we do all this? What's the purpose of all of this? There's just one purpose. Why they design all this? Now, the Hall effect allow them to design a Hall probe. What you see here is a Hall probe. Okay, this is a Hall probe. Because of the phenomenon, the existence of this phenomenon, they understand, they design this Hall probe, and then they use the Hall probe to what? Measure the magnetic field strength. This is the final goal. They want to measure this B. Okay, they want to measure this B. How do you measure this B? Based on this equation, this you can easily measure using your voltmeter, practically, experimentally. I you can easily measure. Thickness you can measure. This one you know. This one is depend on the material. Okay. Give me 1 second. Okay, now just a simple demonstration. Okay, this is my Hall probe. Notice that the Hall voltage is the sign. Magnetic field here, this is the current. They are all perpendicular. They are all not in the same plane. So let's say this is your magnetic field down. This is your current. Where is your Hall voltage? Front and back. Okay, magnetic field down, current is coming here. Hall voltage is front and back. Where is thickness? Parallel to the field. So this is your thickness. Now, if I change, let's say I change magnetic field coming from the front. Okay, from the front. This is magnetic field. This is current. Where is your Hall voltage? Magnetic field, current. Then your Hall voltage is these two sides. Okay, these two sides. Where is your thickness? Magnetic field parallel to magnetic field. So this one is your thickness. This one is your thickness. Okay, so like this, magnetic field coming like this. Current is like this. So your Hall voltage is here and here. And your thickness is parallel to the magnetic field, this one. Okay, so using this one, anywhere, coming from anywhere, okay, you can find this one, T and the calculation. Okay. Now here, I can also take, okay, the relation between VH equals to B like this. I net into B. Okay, so VH is directly proportional to B. I can plot a graph of VHB, or the other way around. What line do you get? This is a constant. The graph for the same probe. Okay, for the same Hall probe. Because this must be constant, right? Same material, same thickness, dimension, same current. I will get a straight line graph. So if you take the same thing, this Hall probe, you put it in one room, in the next room, in the next room. You plot all the data, this is the graph you get. Using this graph, we can calculate, okay, based on what VH I get. This is in millivolt. What VH I get, I can find the B. What did I get? I can find the field strength. Okay, same Hall probe, so it's the same NIT. Okay, this VH, sometimes it can be too small to measure. Sometimes it can be too small to measure, very, very hard to take the reading. Then what do? We have to increase this value. So for VH to be measurable, what do? Based on the formula, we increase the current. This can be increased, or this can be decreased. This can be decreased. There are three ways we can do it. INT. So first step, increase current. If I can increase this current, I increase my chances of taking the reading successfully. Number two, decrease the thickness. So decrease thickness, use a thin semicon, thin slice. Number three, we want to reduce the N. How do I reduce the N? Again, what is the N? Electron per unit volume, charge carrier per unit volume. How do I reduce the N? That is why we use a semiconductor. So our Hall probe is made of semicon because it has smaller N than metal. Question will ask, if I use copper, what will happen? What will be the difference if I use copper, metal, or a semiconductor? The difference is because of the N. One has higher charge density, another one has lower. So semiconductor. That's first way you can reduce the N. Second way you can reduce the N is by lowering the temperature, decrease temperature. Or I can just say use a cold Hall probe. Why use a cold Hall probe? Recall back earlier we mentioned about the semiconductor. The higher the temperature, this is the band. Okay, that is the valence. This is the conduction. This is for the semiconductor. Earlier, we mentioned that at 0 Kelvin, absolute zero, very low temperature, all the electron is in the valence. At room temperature, because higher temperature, some of them gain enough energy, they can jump to conduction. So they jump to conduction. The N will increase as they jump to conduction. How do you make the N low? As low the temperature, as low as I can. So cold Hall probe to decrease the electron available, the number of electron available. Okay, maybe you can add one more, number 4. But this one we have already considered. This is the sine theta. Okay. Make sure that this is perpendicular. The field perpendicular to current I. Okay, why must perpendicular? If it's not perpendicular, this is the Hall probe. If I twist like this is making an angle like this. Okay, if it's not perpendicular like this, that means you have theta. You will have sine theta. Sine theta, what happened to the sine theta? Just now we write BQV equals to QE. That is our equation, right? The magnetic force equals to the electric force. If you have a sine theta here, BQV sine theta, this sine theta will make this smaller. Okay, this sine theta will make this smaller, and this E, you got V over D. This is your Hall voltage. This one smaller, this one will be smaller. So the angle will reduce the Hall voltage. That's why we make it perpendicular. Yes. Okay, the Hall probe we always make it perpendicular. So you can also, if you connect to a voltmeter and then you hold it like this, you get a reading. And then you try to rotate it, you'll see the deflection goes there. Deflection, when you rotate, and let's say you don't know where is the field coming. You rotate and you found the maximum value. Okay, you know that position is perpendicular to the magnetic field. Okay, I think almost everything. One last thing. Just now we mentioned here is N type. What if I switch to P type? Okay, let me erase this. Switch to P type, and how would it change the result? Okay, majority charge is holes. Positive current. Which direction is the hole flowing when I connect the current? See the current is flowing here, positive charge is the same direction as current. So flow will flow in this direction. Positive charge, positive charge. Using your Fleming's left hand, again, find force. Seeing from front, what do I see? This view, magnetic field, current is also X. Whether it is negative or positive charge, doesn't really matter because the direction of the current is still the same. It doesn't change anything. Okay, so it doesn't change the force. The force is still here. Fleming's left hand, feel down, inside, force left. Force is still acting to the left B. So all these charges, positive charges, will start to move left and they build up on the left. Just now it was the electron moving to the left. Now if I change to P type, it is the holes, the positive charge building up. So the polarity switch, here you have negative. Okay, what remain the same? Remain same. Current remains same. Force remains the same. The only difference is the polarity. So if you connect your VH here, here the polarity changes. This is positive, this is negative. Field is still here, current is still here, Hall voltage is still at the side. Okay, does not change anything. Thickness is still, so only the polarity change. That is when I switch to P-type semiconductors. So if you want to know what charge is the one that build up, just look at the majority charge. If the majority is Hall, then it is the Hall that is built up. For the N-type, if the majority is electron, then electron is the one that built up. So the majority charge, depending on what material here, it is the majority charge that builds up. Majority charges.